Hello Gators, this is 2.7 derivatives of cosine x, sine x, and e to the x. And 2.3, we're going to revisit estimating derivatives of a function at a point. All right, relationship between the graphs of f and f prime. If I give you f, can you give me the graph of f prime? And the way to do that is to look at significant parts of the graph, like where the slope is 0. When the slope is 0, that's where you know the derivative has to cross the x-axis. Before this point, the slope is always positive and it becomes less and less positive. So that's what makes sense right here. Over here, the derivative is always negative, and it's going to be the most negative right here where it's the steepest. So here at 4, it's the steepest right here. And then afterwards, the slope is positive, and so we go up there. So this is the graph of the derivative. Now let's do it again. This time I haven't given you the derivative. So we look for turning places because that's going to tell us where the derivative crosses the x-axis. It crosses here, here, and here. Now before this time the derivative is negative. So we're going to have our graph look like this, and our graph now is positive, and it becomes more and more positive and then less and less positive. So it's going to go up and then down. This is all negative. It's most negative right here in the middle. How far down do you go? It doesn't matter at this point because we're just getting a rough picture. And then the rest of the way it's positive. So then we just continue up right here. All right, if I give you the derivative and some of these requirements, let's see if we can't get a picture. We know that the graph of f has to pass through 0, 0, and we know its derivative is -1 all the way through up to 1. So a slope of -1, this is a line that has a slope of -1 up to here. And then we know it's continuous, so wherever it finishes, it needs to take off. And right now, it has to have a slope of 2. So it needs to go up 2 over 1, up 2 over 1. And so this side is going to be a little steeper than the other side. And that fulfills all the requirements. One-sided derivatives. Remember that one-sided derivatives, you're just getting h approaching 0 from either a positive or from a negative side. And that's important as we look at piecewise functions because we're looking at derivatives as they go from the right hand or the left hand. So the derivative can be written as a piecewise function as well, and this will be 2x as x is less than or equal to 0, and it'll be 2 as x is greater than 0. So we know that the equation of the line before 0 will be 2x, which means it's going to cross here at 0, and it's going to have a slope of 2. So it's going to go right up to here. Remember, there is no derivative here because there's not a left-hand and a right-hand derivative that are the same. And then we'll put an open circle here, and then we'll have y prime equal to 2. So this will be a constant here. So there is no derivative. Surprise, surprise. This is a corner or cusp, so we don't get one. Let's take a look at the derivative of the sine function. All right, I'm going to go back to the definition of a derivative, and then I'm going to use some of my trig identities. I'm going to rewrite this, and then it looks like I am going to factor out sine of x from both of these spots here, and I'm going to get this, and then I'm going to notice that the limit of a product is a product of the limits plus the limit of the product is the product of the limits, and as h goes to 0, this has no effect on here, so it's just sine of x. This is limit that we've had before, that goes to 0, which makes this whole product 0. There's no h here, so we know it's cosine, and this is a very famous limit that we know goes to 1. And so here's our answer. Here's our derived function. And we can go through the same operation and we'll find that the derivative of cosine is negative sine of x. All right, now in case you're wondering why calculus uses radian measure, it's because we had to evaluate this limit, and this limit has to be in radians, otherwise the limit doesn't go to 1. All right, another very important limit that I'm about to use is this limit right here. And I drew a picture right here so that you can see that as h gets close to 1 or to 0, that the value right here is 1. And you can look at the table and you can see that as you get closer to 0 from each direction, it looks like we're getting close to 1. So that is that limit. We need to remember that for this next operation. We're going to figure out the derivative of e to the x. We go ahead and use the definition of a limit. I go ahead and use my exponential rules. I'm going to factor this out. Factoring it out gives me this, and now I have a limit of a product. It's a product of limits. This is the limit I asked you to remember. That becomes 1, and we get e to the x. So in other words, the derivative of this function is itself. Derivative of e to the x is e to the x. Okay, so let's summarize. The derivative of cosine x is negative sine x, and the derivative of sine x is cosine x. We're going to use these rules to figure out the derivative. So the derivative of x is equal to, now this is a constant times a function, so this will be 2 cosine of x minus, and this is a constant times a function, so it'll be the constant, and the derivative of cosine is negative sine x. And we're going to clean it up, and it'll be 2 cosine of x plus 5 sine of x. Okay, let me remind you of all these expressions, what they equal. The natural log of 1 is 0. The natural log of 0, well, we can't put 0 in. Remember that the natural log looks like this, and 0 is not in the domain, so this does not exist. E to the 0 is 1, and an e to the natural log of a, remember these are inverse functions, so this is just a, and this exponential inside a natural log will also be a. The derivative of e to the x we just figured out is e to the x. Okay, so let's figure out this derivative, and we're going to use our power rule here. This will be tan x plus, and this is a constant times a differentiable function, so it'll be 3, and then take the derivative of e to the x, it's e to the x. And that's the end of the screencast.